This one's a new one. Spike. Yay, Cowboy Bebop. I'm hitting all the good animes this year. Alright, this one's. You can probably figure out what's wrong with this one without me even telling you. Here's the clip.
Yeah. Heavy Metal Queen. No. That would have killed my face.
Uh-oh, what's wrong? Spike is in space. We all know what happens when people go in space from other movies. They die! They turn to ice, their blood, you know, stuff. This was one of the most fun things I have ever had to research. I didn't have to research, but it was fun. In that very morbidly creepy kind of way, there's two main effects you kind of have to worry about. First one's what's called explosive decompression. That's where you go from a normal atmospheric pressure, like we got into this room, to basically a pure vacuum, which is what you walked into. The other thing is what happens when you're in a vacuum. A lot of these effects kind of overlap, so I'm not going to kind of make two columns like I was originally going to do. I just lump it all together. All of this information came from a paper, 1958, Rapid Explosive Decompression Emergencies in Pressure-Suited Subjects. This was done in 1958 by NASA when they were first getting the space program together. It is a like 100-page paper full of creepy. So these are some of the effects. Severe abdominal pain. You have gas dissolved kind of in your blood, in your innards. You know, back high school chemistry, PV equals nRT. When you suddenly drop the pressure, that means it tries to expand. Ow! Hypoxia, you can't breathe. That means you're not going to be taking in oxygen. You're not going to have any oxygen in your blood. When your blood doesn't have oxygen, it kind of turns blue. Hypoxia means blue. Or cyanosis means blue, hypoxia-related effect. Decompression sickness. Back when we were building the Eads Bridge in St. Louis, 1913 I think it was, they were doing it in pressure chambers underneath the lake, or not the lake, the river, and they come up real quick and suddenly they go, ah! And it killed people. What it was the nitrogen in their blood, same thing as what I was just talking about the first one, it tried to expand, and suddenly you have bubbles in your blood, and you know all these murder shows, you insert a little bit of air or something into someone's bloodstream, it gets to their brain or their heart and kills them. It was killing people. Major right there. We're not just going from under a river to normal atmospheric pressure, we're going from normal atmospheric pressure to hard vacuum. Ow. Alright, next on there. Short and long-term central nervous system damage. That's self-explanatory. Nausea. On top of everything else. Ebolism, swelling, I just mentioned that. This is another way of saying it, but especially tissues that are not elastically able to stretch very much, especially pulmonary tissue in your lungs, your sinuses, and eardrums can rupture. You get about 5 to 15 seconds of what's called useful consciousness, which is the amount of time it takes usually from the heart to pump the blood from the heart to the brain, and then once the heart's run out of blood, there's nothing left to get to the brain, oops, you're unconscious. Actually, you're not quite unconscious. There's residual amounts of oxygen left, and you kind of lose consciousness, and you go through apparently a state that feels like being really, really drunk. I suppose that's good news. So these were some tests that were referenced in that paper. Oh, poor PETA, they're going to have a heart attack with this. They tried some of this out on animals.
Morality percent.
I know, and cute ones like bunny rabbits too.
Sure, they're not human balls.
I know. What's really important here is this column right here, the decompression time. What you can see is they started going from kind of a normal atmospheric pressure to not very much. They did it first in almost a second, and they kept lowering it with all these different animals. This was a whole bunch of studies compiled into one chart. And what you can see with this, as the decompression time goes down, the mortality rate goes up. You can survive it if it's like, you know, less than or more than 1/10 of a second, but start below that, it's going to start killing you. The question is, where is Spike on this chart? Here's another graph from that paper. What this is it's the area of the orifice, that sounds wrong. The area of the hole through which the air is escaping, and the volume of the air that you have. So where is Spike on here? Not here. So what we have is these are lines of amount of time it's going to take air to escape. So it's going to escape between 1/1000th of a second and 1/100th of a second, and this is a logarithmic graph, so it's actually closer to the 1/1000th. So that puts Spike down here. 50 to 100% chance of mortality. Oopsie! Not good. And I actually graphed this, but I couldn't get the thing to export right. I plotted this all up, fit a curve to it, put him on the decompression time in. It turns out he has an 83% chance of mortality. 83% chance of dying. That's not even good odds for Russian roulette. I don't think I would jump out of there. All right. Another thing that you see in movies a lot is people jump out of space and they turn into icicles. How does this work? There's three main methods you can transfer heat. First one, conduction. That's basically if I come up and touch you, you feel warm from me because I'm transferring heat, thermal energy from me to you. Unless I've just been outside, in which case it's going to be the other way around. Another way is convection. This is where, like, if you have a heated floor, the heat starts at the floor, but because it's hotter, it goes up, and then if it's cold up there, it releases the heat, comes back down, and you get this big cycle. It's kind of cool. Ever boiled water? That's what's happening. You ever watch the sun? It happens there too. Kind of cool. Third one is radiation. Basically, we are all giving off photons of some sort. We do it in the infrared. It doesn't carry away a lot of energy, but we can radiate, and that's how we get rid of some of our heat. So how are these going to work out in space? Well, conduction doesn't work. There's nothing to transfer it to. It's a hard vacuum. Convection, there's nothing to carry it, so it's not going to convect. The only thing that's going to work is radiation. But how efficient is it?
Yummy.
Math. Back to chemistry. Specific heat of the human body is 3,470 joules per kilogram degrees Kelvin. That's an awesome set of units. Stick to physics, thank you. This isn't average, this isn't exact. Radiant power of the human body, we give off about as much energy as a 100-watt light bulb. What? Why don't we glow? Why do we have to get glow sticks at the grave? You're thinking probably. The reason is light bulbs concentrate that amount of energy over a very small filament. We are concentrating that over our entire body. We have about 2 square meters of fleshy bits on the outside. So we radiate over a very large area, which means any particular area isn't giving off a lot of energy, which is why we don't glow unless you have an infrared camera. Estimating Spike weighs about 150 pounds. He's kind of skinny and white like me, so we'll go with it. Converting that to units that I know how to use, we'll go with kilograms, 68, and put this all together, and what that turns out, multiplying it together in the way that's going to cancel out the units right to get our degrees Celsius, we get he loses 0.000424 degrees Celsius every second. I trimmed the clip, but he was out in space for about 60 seconds, so multiply that together, and in that time he would have dropped his body heat by radiating it away 0.025 degrees Celsius. That's nothing. So all those other movies where people turn into ice, those are wrong. Cowboy Bebop actually got something right. Wow. But still, summary of all the other stuff. In anime, you can jump out of a spacecraft and be perfectly fine for 60 seconds or more. In reality, you get 15 seconds at best. Anime, he was fine. He just had to take a couple deep breaths when he got to the other ship. Reality, 100 pages of paper. Anime, oh, he jumped out. He must have known that it wasn't going to be too bad for him. Reality, not a good chance. Busted.